Yeah, this is just a small research update for me on some of the work I've been doing on rendering of space-borne images recently for rendering in the loop for a lot of the vision-based navigation algorithms that the lab has. This title maybe is a little bit too broad for the piece that I'm going to present on here, as you'll see, but too bad. This is the larger effort. So toward unified, calibrated rendering of space-borne imagery. The motivation here is that, as we all know, vision-based navigation algorithms enable a lot of autonomous capabilities for passive, non-cooperative navigation in distributed space systems. Cameras themselves offer a very rich sensing modality given their low size, weight, power, and cost. And our own research is, of course, propped up by a lot of vision-based navigation algorithms at both far range for angles-only navigation and close range for pose estimation and shape reconstruction. And as a whole, you need space-borne imagery in order to be able to develop and test these algorithms. So that's the focus of this presentation. Where do you get the space-borne imagery from? So there's a variety of sources we currently use. At the kind of the foundation, the bedrock is real images from flight missions. This is the ultimate reference of what does this data actually look like. And we're fortunate to have direct access to two such data sets from the Prisma and Starling missions here in SLAB. Then next kind of layer up, we have hardware test beds that can augment data we get from real space flight missions. So we have Tron and the optical stimulator in our lab. You guys have all heard plenty of those. And those offer a little bit less realism, but we can actually generate additional imagery with them. We're not limited just to what we have from space missions. And then kind of at the other end, we have fully software synthetic images, which offer the most convenience. This is a term I've totally made up. No one uses this, but I'm saying hi-fi, low-co, lo-fi, high-co. Co stands for convenience. Yeah. I don't know who said phi can stand for fidelity, but co can stand for convenience. And so for our software synthetic images, the lab, of course, has an array of different software tools that have been used to generate images in the past. We have ones focused on stars and distant space objects that's been used for Artemis. We have asteroid rendering that's been used for ANTS project in the past. We have OpenGL reference renderer for the Tron hardware testbed. And we have also OpenGL-based renderer that's used for the optical stimulator. And these each are geared towards slightly different regimes and types of images to generate. And here I've just annotated them with the kinds of ranges that we have of the targets. So this is under the assumption you're looking at another object, or especially you're looking at a spacecraft. Almost all of these sources, all of these image generation capabilities can handle either far-range targets, or close-range targets, or both, but nothing in the middle. So even the ones that can handle both, and that we use for both close, resolved, what we call image rendering, where you can actually see details on a spacecraft, and ones where you just see a point source, the range in between is a little bit challenging, and I'll talk about why that is. The only data set that we really have that addresses that is Prisma, which can give us a sense of this transition from far-range to close-range images. As I just said, that's that. For our hardware test beds, some of their biggest limitations are the fact that they have a limited range of motion. For example, Tron, you just can't get any farther than the geometry of the room. And then in general, they're hard to use closed loop, as people working on RPO kit in the loop know. And then they're hard to scale. They're time intensive and they require people to get trained and build expertise using the systems. And it's not something you can broadly share with lots of people to use in parallel. And then in the software synthetic renderers, one of the gaps here is that currently they're specialized to different uses, not something that you can seamlessly operate between a drifting kind of model of the world through different regimes in a mission, which is one of the reasons you would want a synthetic renderer in the first place, because it's really the only thing that could do that. And then, as I said, we have currently no support for this middle range semi-resolved rendering in the transition from point sources to detailed spacecraft. They also are not always realistic and not always have been calibrated against real flight imagery. Just to visualize the range gap, I was really doing a lot in the range gap because that's what I'm talking about in this presentation. But Prisma is the only thing in between. All of the others kind of far on this extreme of far range or close range. And in the middle, there's a vacuum. That's the closest that you'll get to Justin-style memes in my presentations. So why is there a range gap? Why is it challenging to create this kind of imagery? And the underlying reason for this is that when generating these two kinds of images, we actually use fundamentally different models for creating them. At the close range extreme on the right, we assume we have fully resolved spacecraft geometry. It's at a low spatial frequency, so the ratio of details, spatial size of details on the spacecraft to your sampling frequency, aka your image resolution, is small or large. So you can actually directly rasterize spacecraft details using typical graphical rasterization pipelines. We don't worry about subpixel accuracy because we're more interested in neural network-based architectures where we're identifying macro scale features in the image. On the other hand, when we're doing unresolved point sources, this is used for distant spacecraft and stars. This is a high spatial frequency. A point source is the highest spatial frequency you can get. And so we're very interested in getting a subpixel accuracy accounting for the point spread function of the optical system. So even though these things are point sources physically, they don't show up as point sources in the image because you have an optical system in between, and that does effectively a sort of low-pass filter on the signal before capturing it. Why is this important? The whole thing we're trying to enable here with these kinds of image-based algorithms is rendezvous and proximity operations. In order to rendezvous, you need to be able to transition from one regime to the other, and it's very important to be able to know where one kind of navigation algorithm may break down and the other may start being viable. And so what exactly happens in this range between far and close is something that's really yet to be explored synthetically in closed-loop simulations. So, problem statement of this is a larger effort, but here's the overall vision of what we're working on here, is we want to develop a fully software synthetic renderer for spaceborne imagery that can be used in closed loop, very flexible to different kinds of mission scenarios, that unifies all the disparate rendering models that we have in the lab into a single multimodal renderer for both far and close range. Additionally, to support the middle range, these semi-resolved images, and ultimately, we want to calibrate these against the real flight data that we have from Prisma and Starlink and Tron LEOS. So SLAB as a lab is very uniquely positioned to address this problem because of the kind of pyramid that we have of real reference data and hardware testbeds that we can all leverage to create these high convenience and higher fidelity models. The rest of this presentation is going to be focused on this mid-range semi-resolved part because that's the sort of new techniques needed bit for actually creating good images here. So before talking about the approach used to solve this, we'll do a review of the way we do these two kinds of rendering of the far range and close range. So for close range, we do typical rasterization-based rendering, which is what video games and lots of 3D graphics use. The typical pipeline is called a two-stage pipeline that consists of a vertex shader and a fragment shader. These are two small programs that run on a GPU. You don't have to run them on a GPU, but tools like OpenGL and other graphics APIs are set up to run these on the GPU. And OpenGL knows how to do one thing with this, which is draw triangles. That's the only thing OpenGL can do, truly. Like if you're looking at an image made with OpenGL, it was done by drawing triangles. So in the vertex shader, you send your geometry to the GPU and say, here's my triangles. And you tell them spatially, these are the coordinates of the triangles. That's step one. Then the GPU will rasterize these by taking a sample at the center of each pixel. You can adjust this somewhat, but the most typical and standard straightforward way to do it is you take a sample at the center of each pixel. The GPU will say which of those are inside the triangle. And then once it has that, it'll run the second program, the fragment shader, that says, what color do you want each of these to be? And so your first program, your vertex shader, says, where are the points of my triangles? The second program says, what color is each pixel inside the triangle? And once you have a pipeline like that, you can just really directly render any large-scale images you want because we have a CAD file, you have all of the points on a 3D model, which 3D models are themselves also described in terms of triangles. So you have all the faces of the spacecraft, you send them as triangles to the GPU, and then the GPU will draw them in and say, what color is this part? And you can use the material properties of the 3D model to answer that question, what color is this? On the other hand, point spread function type rendering is used for these point sources that we have, where if you have such a far object that it's smaller than a pixel, you can't use direct geometry rasterization-based rendering, because that geometry may actually move in and out of intersection with the pixel centers. And so you're, just like in DSP, you're trying to sample a high-frequency signal, you're going to get aliasing. And so instead of doing that, we account for the point spread function or the filtering of the camera before the sampling step. And so we can directly render, okay, what is the point spread function of the optical system at this location? And we just paste it onto the image, turn on the pixels accordingly. And that's how we render stars. And in OpenGL, we do this by just sending two triangles that cover the area where the star should be. And then when OpenGL says, okay, what color do you want each pixel to be? We can evaluate the point spread function relative to the physical location of the center of the point source. And then we say, okay, it should be that bright. Currently, the renderer just uses a Gaussian model for this. That's the model that's been used for many years in the Starling and Artemis angles-only navigation synthetic imagery. Some recent work by Mike has explored a higher accuracy point spread function model by calibrating against images from Starling. Those have not been yet incorporated into the OpenGL render that we're working on, but they should be. So what's the challenge for semi-resolved rendering of a spacecraft? If you try to render a 3D model of a spacecraft at a large distance, you get this flickering. And that's, as I was speaking about, you have the spacecraft geometry just moving in and out of pixel centers. So the GPU is still just saying, what triangle do I hit at the center of this pixel? And that may be a brightly colored object. It might be a dark part of the spacecraft. It might be no part at all. And so you get a very noisy, very aliased signal. Even if you blur it, so this is a upscaled and blurred spacecraft, you're still blurring a noisy downsampled signal. And this is what you get if you, for example, use the optical stimulator right now on a distant spacecraft. So if you draw a small spacecraft on the optical stimulator, you're still using a rasterization-based pipeline. And so you are getting the impact of the optical system in the optical stimulator, but it's not on a physically accurate model of what light should be coming into the camera because it's already been downsampled and aliased by the rendering pipeline. So what you really want to do is, if you've done DSP, you know you need to filter a signal before you sample it, not after. And so that's the aim of this work. So the new method for semi-resolved rendering that I've been playing with consists of these 6 steps. First, we render the image without the target spacecraft at all. So you can do the stars, whatever other background you want, but you render the sky and the stars using the techniques we already have. Then you determine the bounding box in the image subpixel, less than a pixel. It doesn't have to be pixel aligned, just like physically where is the bounding box of where the spacecraft geometry should be. And we then compute a new asymmetric projection matrix. So the whole image had an original projection matrix. We ask, what's the tiny slice of this projection matrix that would intersect with this bounding box? And we then render the target spacecraft at full resolution into a few thousand by few thousand size image at that tiny projection matrix. So you can imagine this, you can think of this as looking through a really long telescope at the target. So if your target is 10 kilometers away, in theory, if you had a perfect, really good telescope, you could zoom it up to your whole image and render that and get what it should look like just based on the rays of the light. We then filter and downsample that target image to the original size of just a few pixels, and then composite that onto the full scene. So to visualize this is a small section. I've already zoomed in this a lot. This is a small section of an image of where a spacecraft should be. So we render it without the spacecraft. We then say, okay, where should the spacecraft be? That's where its true geometry would be if you could see it perfectly. That's obviously going to be aliased at the size of these pixels. So we blow it up and we render the spacecraft in the orientation it would be. And this is brightened to account for, I'm working on the relative luminosity calibration, but right now I'm just drawing a brighter version of the spacecraft. Okay, we render it at full resolution. Then we do a series of downsampling and filtering passes to gradually blur the image to the size and resolution that it would be if we were to put it there. And then we take that and we composite that result into where it should be in the image. And for the rest of this, I'll just do a demo of running what this looks like. So I have basically the shirt trajectory. So I'm using the shirt ROE2 attitude trajectory, but I've just artificially modified it to start at 1 kilometer distance instead of right in front of the viewer, and then over the course of the trajectory, get closer to the viewer. So these are the shirt images. These are the ones that were generated on Tron. This is a synthetic version of it on the right, and I'll zoom in on where the spacecraft is here, which is right there. So that is the result of doing a full-size rendering of the spacecraft, then filtering and downsampling it progressively over 8 passes to the size that it should be on the pixels, and then compositing it into the original image. This is done accounting for the transparency and depth of the spacecraft. So you could have multiple spacecraft overlapping, and in theory, you should be able to still use this technique with them too. So you can see it kind of getting closer as we go over this trajectory and gradually coming into view. And at some point, you can recognize that it's starting to look like Tango. And I have also, just for the sake of this demo, again, this is calibration work still to be done, but for the sake of this demo, I am just manually doing like an exposure curve that turns down the overall exposure of the image. So both the spacecraft and the stars have the same exposure applied to them. And so as it gets closer, I'm just scaling down the exposure. And so the stars are fading out. But so that's that. Gets closer. You can see there's no flickering. So this is because we're rendering at a large size first and then downsampling it. So that's that. And then just for a comparison, I'll get rid of the semi-resolved pipeline and show you what it looks like instead. And you get that. So there's the spacecraft at 1,000 meters, which is not, you can't really see it most of the time because it's just smaller than a pixel even. And once it does come into the view, so it is getting closer, it'll start to take up the pixels, but you can see that as the spacecraft geometry moves in and out of the sample points, you just kind of get a bunch of noise. So if you were to try to do angles-only navigation on this, you'd have a hard time. You would not be able to do your centroiding of clusters. So that's the demo. And just kind of wrapping up, talking about future work, going back to the problem statement. This technique, I think it needs to be refined, but this is kind of a foundation that can be used for accurate rendering of spacecraft geometry at any distance, and that handles the transition from far range to close range. We will need to do further tuning of it against flight images. So especially from Prisma, again, that's the data set that we have that actually gives us information on what this should look like. But fundamentally, this kind of technique sets the foundation for what that work will look like. And so that's what still needs to be done. Luminosity calibration and point spread function calibration from images from Prisma and Starling. So that's all. Any questions?